It's a couple minutes after 10. Hopefully some people will join us. I will record this as always. Hopefully you're all doing all right. Everybody's muted, so I don't know. Today I just want to kind of the next thing what we've done so far with Trig and these identities is simplifying. The next step is proving where you're given two sides to an equation. And with the two sides, you have to be able to make one side equal the other. Somebody's having breakfast. Oh, hi, Madison. Somebody. Did you just wake up?
Yes.
I'm sorry. It could be worse. I've been up since 5. But that's a choice. So these are kind of some steps that we want to do. With an identity, you're going to be given a left side and a right side, and you have to fundamentally simplify them, do what we've been doing for the last couple of days until they equal the same thing. So these are some hints. I went and found, they're down here, they're Mrs. Legier's strategies. And I'm going to put this up there. Make substitutions. Put things in terms of sine and cosine. If there's brackets, expand. Separate fractions if it's a multiplication thing. If it's an addition or subtraction, you're going to need a common denominator. Sometimes factoring. If we had all sorts of time, we could talk about rationalizing the denominator. Okay, I am sharing my screen. I just wanted to make sure. So it's regardless, it's all kind of the same process. I keep seeing something out the window move. So when I get distracted, that's what it is. Sorry. I'm going to do this with putting pi over 3 because you can do that, but mainly I'm just going to look at using an algebraic approach. Who cares about verifying if it's true or the graphing calculator? Show it algebraically, because when we look at identities, that's normally what we're going to be looking for. So this first one, if we can get this in here, I've got to kind of go move my mouse around to make it work. This one says put pi over 3 in and evaluate unit circle stuff. So 1 over cos of pi over 3 minus cos of pi over 3 sine of pi over 3 times tan of pi over 3, which we can all pull out. We can pull out our unit circles. 1 over the cos of pi over 3. The cos of pi over 3 is a half minus the cos of pi over 3 is a half. Brittany took Ben outside to do something, and he's already back inside. Oh, it's cold, so that's probably her. 1 over a half is 2 minus a half. If you have $2 minus a half a dollar, well, this is 4 over 2 minus, well, that was a really awful half. So this is going to, oh, okay. I don't know what, he's going to come to play something. So that side is 3 over 2. The sine of pi over 3, let's make sure I've done that right. I'm just kind of doing my unit circle in my head. Pi over 3 is there. Yeah. So this is the square root of 3 over 2. Tan of pi over 3 is the square root of 3 over 1. Root 3 times root 3 is 3. 2 times 1 is 2. And some people say left side equals right side. He gets to play games. You guys get to do trig. So we can do that. I'm not going to get you to do a lot of that because I know you can all put numbers into an equation and evaluate, and that's arithmetic. If I'm looking at cos, and I'm going to change that to theta minus cos theta, and the right side is sine of theta, whoops, tan of theta. Restrictions, we can talk about that. When is cos theta cannot equal 0, and then we have that. That's going to actually be the same thing because tan involves that cos. We could figure that out, but I'm more concerned about what we can do with this. So some people like to do one side, some people like to kind of go step by step. Looking at this one, when we have a subtract, and then this is a multiply, this shouts to me common denominator, because we need a common denominator here. So if I have cos of theta and 1, my common denominator is cos of theta, so I'm going to multiply this by cos theta over cos theta. This part doesn't change, minus cos squared theta over cos theta. So that puts it all over one thing. 1 minus cos squared theta. And I'm going to kind of just leave that one there. So that's the common denominator part. This one on the right-hand side, I see a tan, so I can say tan is sine of theta over cos theta. Well, fraction, I can multiply that out, sine times sine. Sorry, I forgot all sorts of equal signs. Is sine squared theta over cos theta. So I get down to there, the denominator's the same, but our numerators are a little bit different. However, when we're dealing with squareds, we can go over and deal with, I'm going to just erase to make that a little bit clear, sine squared plus cos squared equals 1. So depending on how you want to do it, if you move that over there, sine squared theta equals 1 minus cos squared theta. That relationship with that Pythagorean identity, I can use either one. Personally, I think it looks prettier to say I should have done that in a different color. So if I do that substitution, I get sine squared theta over cos theta. Now are those two the same? Someone unmuted and it made quite the noise. But that's kind of the gist of a lot of this is it's manipulation. It's playing with, sometimes you only have to do one side, sometimes you have to do both sides. And like in this one, we had a common denominator, and then we had just a simple substitution. With trig identities, if any one of these, the odds that I've seen them, because it's been a little while, but I know my basic identities, and it's just about using those and playing around. There's no experience for trig identities other than experience and doing them and doing them and doing them. So I'm not going to worry about putting stuff in. We've got sine of x over tan of x equals cos of x. Sine theta over tan theta. So when you have one like this that is relatively straightforward, I'm going to try to do as little as possible with that because cos theta is nice and simple. I'm going to do here, just put in sines and cosines. Tan is, oh, can anyone hear them playing their game over there? We're trying to teach Ben his letters. So
Yes.
it's kind of a spinner pick letters like tic-tac-toe game. He understands the letters a little bit. He doesn't really understand the strategy. So fraction over fraction I don't like. Sine of theta times the reciprocal of that is cos theta over sine of theta. Oh, and Kate's a little cranky. Now, we get down to sine of theta over sine of theta. Those cancel. Cos of theta. Left side does not equal right railroad. Right side. And those are the same, and we're done. So far, so good. A lot of this is just going to be trying. If you're not practicing these are going to get tricky. If you are practicing these things, hopefully they get a little bit more straightforward. This one looks kind of intimidating because you've got all sorts of stuff and something relatively simple. This I don't particularly like. 1 over cosecant is 1 over sine theta, which is just because we can flip those over. So ultimately, we want to make the right hand side or the left hand side, all of this stuff, we want to make that look like sine theta. Sine theta and cos squared theta plus sine cubed. Can I move that a little bit to make it? So one of the strategies, whoops, sorry. This way, if I cover both ears, I don't have to hear as much. Is there a common factor between sine theta, cos squared theta, and sine cubed theta? Yep. We have a common factor of sine theta. If I factor sine out of this business, cos squared theta. If I factor a sine out of sine cubed, if you're trying to take an x out of x cubed, you're left with x squared. So we get that. Does anyone remember what cos squared plus sine squared equals? Oh no. That's weird. So we know from the Pythagorean identity that is 1. So we can, anytime you have an expression that has cos squared theta plus sine squared theta, you can straight up switch that whole business and put a 1 in there. So therefore, this is sine of theta times 1, sine of theta, and the two sides equal each other, and that's it. So far, we've looked at ones that we don't have to do a lot of work to both sides, um, but that is possible. And if I had time and didn't spend this morning chasing two wild toddlers around, I would have probably looked at some of these. So I could run into one and say, oh my gosh, I don't like this, and all of that. I can stumble. That's the joy and pain of trig identities. So I think I just have, because we're not going to worry about solving, I just have a couple more to do. Sine A, tan A, prove that this is an identity. So this means we have to prove that the left side equals the right side. I don't like this part. I'm actually, just to give myself more space. Wow, that was way louder than I expected. I'm sorry. So I want to prove this. I'm going to do something here. Oh, there's all sorts. Whoops, need a pen. Left side, right side. Well, 1 over cotan A is really just tan A, which this is all kind of semantics. So if we can get this side to equal any one of those, we're good. Sine A plus tan A over 1 plus cos A. We don't necessarily have to have a common denominator. I'm going to take that out of there. There's also that one that we can play with, that sine A plus cos A over 1 plus cos A. I see that cos A, and I know I need a cos A in the denominator, and I know I need just a cos A. So I'm going to make the denominator for everything cos of A, which means we need to multiply this by cos A over cos A. Well, this I can just, well, technically we're, and this is an instance where this could be a horrific strategy, but it's all about trying stuff out. Big fraction, so cos A sine A plus sine A all over cos A. Over cos A. I think I've got everything there right. Sine over cos. I don't like this fraction. Cos A, so I'm going to rewrite the first one. Times the reciprocal of this one is cos A over cos squared A. I can straight up get rid of those. Oh, I think I see it. So my numerator is now over cos. Now I have a common factor here. Whoops. The common factor of the numerator is sine A. I would be left with cos A plus 1. The common factor in the denominator is cos of A. I don't know if you can hear that. He likes to cheat. He's 4. This is bad news. Hey, look at that. Is cos A plus 1 and 1 plus cos A the same? X. Goodbye. Goodbye. Oh, equals, equals. This one's a little bit tricky. So all we're left with over here is sine A over cos A, which, if we go way back up here, is that what we wanted to make it look like? Every time teaching these, it's always like, oh, unless it's one that I've done before. I mean, I've straight up messed these up in front of classes, and had to start over. Hopefully we don't have to do that because I don't want to take up too much of your time, just so we can see the whole page. And sometimes this works out wonderfully. That one there is like anything with a sum where we have to use common denominators and all of that tends to be a little bit trickier. If it's products and Pythagorean identities, it's usually a little bit more straightforward. And we can, I think that, let's go back here, zoom, page width. So that was a little bit sneaky. Now when we see the squareds, anytime you see the squareds, this is where we should be looking, because then we can do some more manipulation. I don't know why I switched. So the squareds usually mean Pythagorean identities. So I'm going to, again, just cut that out. What am I looking for? Why am I doing that when it's right here? Just because I write large and it's just easier. For me. So which side, whoever wrote this book likes to leave the right side is cosecant. I'm going to leave that alone for now because it's one thing. So that's where I start when you, oh, it's almost where you start. Theta minus 1. When you have a 1 and one of these squared things, that's where we want to go back to this page. So I've got secant squared. So I'm just going to say 1 plus tan squared equals secant. Switch the page. So I'm just going to write up over here 1 plus tan squared of an angle secant squared. So I have secant squared and I have a minus 1. Minus 1, minus 1. So now that I see that, I can rewrite over here. Give myself a little bit of space. Secant squared theta over tan squared theta. Now, when I get to a spot like this, when I have secants and tans, this is where I'm going to go. What's the word I'm looking for? Put in signs. What did substitute sign? Sines and cosines. Secant squared is 1 over cos squared theta. Tan squared is sine squared over cos squared. So when I get to that, a fraction over a fraction looks awful, but we can say this is 1 over cos squared multiplied by the reciprocal cos squared theta over sine squared theta. The cosines now cancel, and we're left with a 1 in the numerator, 1 over sine squared theta. Doesn't necessarily look like that, but we know that cosecant squared is 1 over sine squared theta. Could you say this equals, as long as you have this and that, or that and that, we can say the left side equals the right side. And then if you're old-fashioned like me, when I was in high school and did these, we had to put QED, which is a Latin phrase, quod erat demonstrandum. That has been proven or demonstrated. But that's just old lingo. So that is it fundamentally a lot different than what we've done the last couple of days? Not really. It's just you have to set one side to the other, and it's all going to be these relationships, which are on one of the pages. Is there any questions? So, that's what we did. What? Oh,
Sorry. How did you find those restrictions earlier
the
in those questions?
like
Way back.
way back here. Well, a restriction like this comes out of like a fraction. The denominator can't be 0. So you can go through and do all of your simplification. This is the denominator ultimately is cos theta, so cos theta can't be 0. So cos of theta, the angle cannot be cos is 0 at pi over 2. Like if we really want to get picky, but ultimately that's where we need to get to. I'm not too worried about the restrictions at the moment just because I mean there's the restriction here is sine squared cannot be 0. Well, if I take the square root, sine of theta cannot be 0. Theta equals 0. Because it's 0, pi, 2 pi, 3 pi, and all of that. Does that make sense?
No, I'm even more confused. What? Why are there all those letters at the end? K.
Mr. McKay, I'm so lost. Like,
E.
you didn't even know.
Kit,
Me too.
Like, we should just like skip trigs.
so the restrictions thing is about fractions, right? Can a denominator, for the restrictions, I'm not going to ask you right now. When you did pre-calc 11 last semester, you did rational functions, right? So you could end up with like x plus 2 over x minus 1. What's the restriction or non-permissible value here? Where can we have the problem when x equals what?
Positive one.
Positive 1. The denominator can't be 0, so with algebraic or polynomials, we just said x minus 1 can't be 0, so x can't be 0, and for a, no, x can't be 1. For a polynomial, that's only one spot, but sine of theta as a function, oh, this is going to be really bad, repeats over and over. So we have 0, we have pi. So that's what all that business is. Really, the restriction, sine can't be 0. And then, but I'm not going to ask you that. I'm going to say, can you simplify? Wow, that one's a little bit rough. That one's a little bit fractions. Oh, hey, there we go. That one should be okay. Practice. That one is going to be Pythagorean stuff. Let's see what Mrs. Lishy. Some of these are like this is the crappy part about uh, not being able to sit and you guys start practicing while I'm sitting there. This page here is new. This is one that I stole from Mrs. Legier. Let's, instead of worrying about some of the ones in here, but it's all about practicing and trying, and we're just trying to, my kind of goal is to expose you. There's the word I was looking for, expose you to trig identities. So I want to go over, this is Mrs. Legier's. I would start with like, I don't know, maybe those first 4. Because they're all, some of them are, well, there's a common factor in there, there's a common factor in there. Anytime I see a plus, I want a common factor. But I would start trying some of those if you have some time today. Tomorrow, I'll go over a handful of them, but we're not going to, we can't do a whole pile. What do you need to know about them? Well, you need to know that trig identities exist. I had some questions wherever that Teams thing is in here that is more from that first section, which is just about simplifying them. But that's what I want you to be able to do. And that's just the document that says do the questions that are in there. So I'm going to save this and upload it. If you want to try some of those tomorrow, I'll do that. Hi. Kids are great. So are there any other questions?
Okay.
Yep.
So, you want us to do, wait,
Oh, so you want to see those other questions, like those, like the ones that are in that document, like from the booklet thing?
So, like, if you want to practice these, like today, going to tomorrow, like, look at these, and I will upload these questions in the. It'll be in this particular file shortly. The assignment that it's like, okay, if you want to get the credit, you need to try, and the assignment questions are all in this particular file as well. They're just the questions from that first section, which I think
Okay,
if
so
you
it's not all of them right now. It's just like
no,
ones that are given on that document.
yeah, like the assignment are these ones that are kind of highlighted that are listed that do on a piece of paper. Take a picture, and some people I think have figured out how to submit those. But the ones at the end of here are just like practice, and I'll go over some of these tomorrow. Because Trig Identities is this really crappy thing that it's just like I look at these because I have more experience. That is a factoring thing, I think. There's a lot of this involves factoring and sines and cosines. That is taking tan being sine over cos. That is putting sines and cosines in. That's an expansion. That could be an expansion with sines and cosines, but I'll go over some more tomorrow. I don't want to spend piles of time today. But again, it's just these are the things, and this is trying to condense 2 weeks, maybe 8 to 10 classes into kind of 4 days, 5 days. So, and like we would do quizzes, we would do all sorts of stuff where you would have a whole class to work and do stuff with each other, where now you're isolated, and unless you're FaceTiming with your math, which some of you might be, but my guess is most of you aren't. So I don't want to take up any more time. I'll come back tomorrow and I'll upload and save everything, and so you can watch it if you need to. Um, and I will, I think, have more information about credit versus that. We have a staff meeting this afternoon, so I can give you some more information on that. But most of it looks like it's like, well, it's at the teacher and the principal's discretion, which really means it's at the teacher's discretion. And we'll see what if I don't see anybody ever around in here. Okay, you can't do the trig questions, but you can do all of the other questions, and I knew you could do that going forward. Well, sure. Some people don't like trig identities. Some people don't like trig in general. So it's not like we've got 2.5 months, give or take. Um, we'll get some stuff done. If you guys do some work, we'll be good. So are we good for today? Suppose I can answer give some of that a shot. I can answer some questions tomorrow.
Oh, okay, I have so many questions. I'd drive you bonkers.
No, that's all right. If we have to, we'll get some stuff done, and it's just the most. Hey, who knows? I saw yesterday they might relax restrictions in terms of government stuff. So school's not going back because 700 people in a building is just too much. But we'll get as much stuff done as we can, and hopefully we all get credits. And if we need to, we'll get you guys through. You guys are all smart and capable, so I have faith in all of you. So we're good for today.
Yes, thank you.
All right. I'll see some of you, talk to some of you this afternoon, and some of you tomorrow. Adios. Have a good afternoon.
Thanks, Kate.
No problem.